All right, so today we're going to be talking about types of nuclear reactions. Those two types are fusion and fission. So, if we think about the word fuse, hopefully that means to you that you're putting things together. And so, the word fusion also means the same thing. It means we're going to be combining things. Fission is opposite of that. That means we're going to be splitting something apart. And so the thing to remember with both of these is that these are types of nuclear reactions. So nuclear reactions involve the protons and the neutrons that are located in the nucleus. So we're either going to be combining something to make a new nucleus or we're going to be splitting apart a nucleus. And if you remember, both of those released an enormous amount of energy. All right, so let's get started. Let's talk about nuclear fusion first. So, it's when you have a small amount of mass transformed into a very large amount of energy by joining together atomic particles. And this is a process that takes place in the sun. So, what happens is you have a hydrogen plus another hydrogen. So, these two hydrogens end up combining, they join together, they fuse together, and they make a helium atom. And in that process, they also release a neutron, but it also is releasing an enormous amount of energy. Okay. So, let's watch a video and see what it shows you a little bit about how this is happening in the sun.
If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get two atoms to fuse. Two protons have the same charge, they're both positively charged, they want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse, and that's very, very rare.
To force protons together takes immense amounts of heat and pressure, generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
But with gravity crushing things down, things get close enough together, and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
Whoops. All right, let's get back over here. All right, so that's how fusion works in the sun. So here's another picture. So it's showing you that you have hydrogen and another hydrogen. They're coming together. They're making this helium atom. Okay. And up here it says the sun is a giant ball of hydrogen. So that's where all the hydrogen is coming from. So let's read number 2 here. It says inside the sun, the hydrogen atoms are heated so much that they turn into a plasma state where the electrons are no longer orbit the protons in the nucleus. Um, so the freed nuclei then fuse to form helium atoms and neutrons. And so this fusion releases a huge amount of energy as a result. All right, let's talk about nuclear fission. So this was opposite of that. So this was splitting apart an atom. So we have a small amount of mass who's converted into a large amount of energy by breaking apart a nucleus. So we have a uranium atom here, and then we have this particle here that is going to hit your uranium, and it hits it enough to split the uranium apart. And so when gets split apart, you have two new different elements. Plus, you have other neutrons that are released as well. Okay. Um, so this is the process. This nuclear fusion is the process that is used in your nuclear power plants. All right. So basically, what happens is you have a large atom of one element split into two smaller and different atoms with resulting release of free neutrons and energy. Let me go back just a second. This atom right here, this uranium, this would be considered the parent atom. And then these two new atoms would be considered the daughter atom. All right. So it's it's what that original parent atom is broken into, that's going to be your daughter atoms. Okay, and so uranium ore is going to be the mineral used in these power plants. And so uranium ore is a non-renewable resource in the Earth's crust. So that means that we mine for it, and once we use it all, it doesn't replenish itself. That's what non-renewable means. And so, in a nuclear power plant, they have something called a nuclear fuel cycle. That involves producing the fuel used in the nuclear reactors, and it also is producing the fuel used in disposing of the radioactive waste. Because when we're dealing with nuclear, the waste that we get is radioactive. And we're going to learn that it takes a certain amount of time for these radioactive atoms to decay to convert into a more stable atoms. So uranium is found in Australia, Africa, North America, and there's three isotopes of uranium. And so we've worked with isotopes. We know that the one that is the most abundant is the one that we find on the periodic table. So that's uranium 238. We have uranium 235, that's about 0.71%, and then uranium 234 is about 0.01%. The one that's used in your nuclear reactors at a power plant is going to be that uranium 235. Um, but in order for it to be used in that nuclear reactor, it needs to have a concentration of about 3%. So it goes anywhere between 3 and 5%. So what they need to do is they need to take it through a refining process, and that refining process is called enrichment. And so it's a pretty detailed process. If you click on this, I'm not going to do it right now, but you can do it on your own time. You can actually, it'll link you to the whole process of how they go through the enrichment. It has to get converted into a gas, and then they do some more stuff to it. So there's a big process in doing that to get it up to that 3%. All right, so after enrichment, then the uranium fuel is going to be used in the nuclear reactor, and they end up making it into these very small uranium dioxide pellets. Okay, so it looks like this. This is what uranium ore looks like. And so, in that enrichment process, if you go back and look at that website, it actually will show you once this is all broken down, it's like a yellow powder, it's a yellow dust. All right, so each one of these pellets is going to be equivalent to a ton of coal. So that's an enormous amount of energy sitting in one of those pellets. All right, so then those pellets are going to be placed into a fuel rod, which are going to be closed pipes that can be as long as about 3.7 meters. So if you're not familiar with meters, I put in 12 feet there. So that's a good size. So you're going to put all these pellets in there. And then those fuel rods are going to be put into this square fuel assembly. And usually they have around 200 rods. Not all of them contain 200. Some are less, some are more. But a typical one is going to contain about 250 fuel assemblies. So doing the math, if we have 250 assemblies times 200 rods, that's about 50,000 pellets of uranium. And each one of those pellets was equivalent to a ton of coal. So that's a lot of energy in that one fuel assembly. So what happens is you have a neutron, and so it's important that I mention that when this is happening in a nuclear power plant, it's a controlled process. So that means somebody is controlling when they're releasing neutrons and when they're not. So they can send them out fast, they can send them out slow, or not at all. And so the neutron, we say, is the bullet that starts the nuclear fission process. So the uranium 235 that was enriched is going to be bombarded with those neutrons. And when the nucleus of an atom of uranium 235 is hit by and absorbs that neutron, it's going to become very unstable. And as a result, it's going to split it into two smaller ones, which are roughly about half the size of the original uranium. And then not only do you get those daughter atoms, you also get a few neutrons that are going to be ejected from the uranium atom. And so what happens is you end up getting something called a chain reaction. So then those neutrons that were released, they're going to go and hit more uranium. And then that uranium is going to split. So it's going to split into daughter atoms. Plus, it's going to also release some more neutrons. And so this process just keeps going on and on and on. And that's why we call it a chain reaction. And so here's a picture of it. Here's the neutron, hits my uranium. So this would be like my parent atom here. And then these are the daughter atoms here, these fragments that are coming off of it. And then you also get these free neutrons. And so those are going to be flying around. They're going to hit another uranium. And then that uranium is going to split apart, again, releasing more neutrons. Same thing's happening down here. I have this neutron. It hit this uranium and then split into two atoms. And then you have free neutrons there. And then this process just continues and continues and continues. They have something within the reactor that will collect or basically pull those neutrons towards it when you want this reaction to stop. Okay, so um, the person in charge of all of that is controlling how many neutrons and how long this reaction continues to happen. Okay, so the fission of uranium-235, like I said, it releases a lot of energy in the form of heat, which is going to be used in the power plant to transform water into steam. And then that steam is used to generate electricity. And like I said, this is possible because that fission reaction is controlled with those neutrons being sent out and then collected. So nuclear bombs are going to be a result of something that's uncontrolled fission. So a bomb-like explosion can't occur at a nuclear power plant because the nuclear fuel used is only about 3% of that uranium-235. And if to be bomb grade, it would need to be about 20% uranium-235. All right, so a little bit of a recap. These reactions in a power plant can be started and stopped. They can be increased or decreased. And so that allows for the desired amount of heat energy to be produced. All right, so we're going to watch this video real quick on fission, and then we'll be done with these notes.
Hi, I'm Emerald Robinson, and in this What Is video, we're going to discuss nuclear fission. Nuclear fission is defined as a reaction in which the nucleus of an atom is split, releasing energy and radioactivity. Fission occurs when an atom of a heavy element, that is, one that has a large atomic mass, splits into atoms of lighter elements. The products of the reaction have less mass than the starting atom. This difference in mass is accounted for in the energy and radioactivity released. Let's look at an example. Uranium-235 is a naturally occurring radioactive element. In a typical fission reaction, uranium-235's nucleus absorbs a neutron moving at a low speed. This neutron causes the nucleus to become reactive or to destabilize. The destabilized nucleus splits, transforming into lighter elements like krypton and barium. Energy and radioactivity are released, as well as multiple fast-moving neutrons. These neutrons can then go on to start another reaction with more uranium atoms. Because the reaction starts again by itself, it's called a chain reaction. An uncontrolled chain reaction releases huge amounts of energy and is what powers atomic bombs. Humans have learned to harness the energy from controlled fission reactions. In nuclear power plants, the heat energy released from the uranium fission reaction just described is used to turn water into steam. This steam is used to turn turbines, which in turn generate electricity. Engineers control the rate of fission by using graphite rods to absorb the excess neutrons produced. Energy produced by nuclear fission is used by humans all around the world. Unlike burning fossil fuels, fission doesn't release carbon dioxide into the air, so it doesn't contribute to global warming. However, using nuclear power generates radioactive waste, which makes it unpopular with some people. Fission is a powerful force of nature that man has just begun to explore.
Okay, so that wraps up the notes on fission and fusion.